Good morning, everyone. Welcome to today's class. Today we are gonna continue on chapter number 7, digital circuits. Okay. So in the last class we talked about the sign extension and the synthesis of logical circuits. Right. Sign extension is a very simple. It's a very simple concept. Um, if you want to extend a binary number to a desired size or desired length, then you can use sign extension to achieve that goal, right? For instance, if you have a positive binary number, if the binary number you want to extend is a positive binary number, then you just need to add zeros in front of the binary number, right? For instance, if we have positive 5, um, the normal from that will be um, 0, 1, or 1, right? I'm sorry. Oh, that's right. 0, 1, or 1. And as you can see, it's a 4-bit. It's a 4-bit binary number. And if you want to extend this binary number to 8-bit, right, we just need to add 4 zeros in front of it. And the result is going to be a 4-bit positive 5, right? For negative numbers, we add ones in front of the binary number, right? For instance, if we have minus 5, right? But first you need to write what is the minus 5. So here let's also review how to write a negative binary number. To write a negative binary number, we first write the positive form, right? In the first step, we write positive 5. Second step, we flip the bits. Third step, we plus 1 with the flipped binary number. And the result is 1011. That is minus 5, right? Right, so, and as you can see, this is a 4-bit. This is also a 4-bit binary number. And if you want to extend it to 8-bit, we just need to add 4 ones in front of it. And the result is a 8-bit negative 5 in the binary form, right? Alright, so that's the sign extension. And the second concept, or the second topic we introduced last time, is the synthesis of logic circuits, right? So what that means? That means if you have a logic expiration, or if you have a truth table, right? And we want to find the logic circuit implementation. In other words, if the question gives you a truth table or logic expiration, can you draw the corresponding logic circuit, right? The simplest example would be if the logic expiration f equals to a times b, then the implementation of this f is just a simple AND gate, right? So that's the one from. The other from could be if the question gives you a truth table and it tells you the output of f, right? And let's say if that is the output of f, from here you should also be able to find what's the logic circuit implementation, right? But if you have a truth table, then we have 3 steps to realize a truth table with a logic circuit, right? These three steps are, the first one is we find rows that are outputting 1, right? That's the first step. Second step is we write a logic product of these rows with inputs or the inverse of inputs. Okay, and the last step is sum them together. So what that means, let's use this simple example A, B, F. Okay, 2 inputs and 1 output. The truth table of this logical circuit is 0, 0, 0, 1. Okay, just like the example I showed you before. Right, so the first step, we focus on rows that are outputting 1, which is the last one. So for referring convenience, let's label these rows. Okay, let's numbering these rows. Let's count from 0 to 7. So that will be 0, 1, 2, 3. Correct. All right. After that, then we have row 3 is outputting 1, right? The second step, we write a logical product of these rows. So row 3 can be represented as A times B. Why? Because row 3 is 2 A's, right? And A means the original input. 0 means the inverse of input. In other words, it either be A bar or B bar, right? But here we have 2 A's, so that means we have the original inputs, A and B. Alright, the last step is we just need to sum all rows together. Here we only have a single row, so F equals to A times B. Okay. And after we have the logic expression, the logical circuit is easy to draw, right? We just need to draw A and B and an AND gate, because here the operation is AND, it's logic AND, right? All right, so that's just a very simple example. Here let's see a more complex one. For instance, if we have 3 inputs, okay, if we have 3 different inputs A, B, C, and a single output D, F, okay, for 3 inputs, the truth table will have 8 rows, because we have 8 different input combinations, right? Starting from 0, 0, 0 to 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and the last one, 1, 1, 1, right? If you don't know how to list these rows, I teach you a simple way to list these 8 rows. The simple way is, if these rows are following increasing decimal numbering system. For instance, if you treat the first row, or if you treat all rows as a 3-digit binary number, okay, then the first row is representing decimal 0, right? The second row is representing decimal 1, decimal 2, decimal 3, 4, 5, 6, 7, right? We can pick one to verify our thought. For instance, row number 4, the corresponding input combination is 100, and 100 is equivalent to decimal 4 if 100 is an unsigned binary number, right? All right, and then for the output, for the corresponding output, it is 1 0, 1 0 0, and 0 1 1. Okay. All right, so let's follow these 3 steps to find the logic expression and the corresponding logical circuit. Alright, so the first step, we need to focus on rows that are outputting ones. So we have row 0, 2, 6, and 7. These 4 rows are outputting ones, right? Alright, the second step, we need to use logic product to represent each row. For row 0, we have 0, 0, 0 as the input combination. So the corresponding input is, so the corresponding logic product is A bar, B bar, and C bar, right? Row number 2, we have 0, 1, 0. So the corresponding logic product is A bar, B, and C bar. For row number 6, we have A, B, and C bar. For row number 7, we have A, B, C, because we have 3 A's as the input, right? Alright, so after we finish this step, as you can see, we have 4 logic products. And the last step is we just need to sum them together. So F equals to A bar, B bar, C bar plus A bar, B, C bar plus A, B, C bar plus A, B, C, right? It's a long expression, but it's not very complicated. The whole process is not very complicated, right? Right. Then after we have the logic expression, we can draw this logical circuit. The simplest way, or the more the most organized way to draw this logic circuit is we put 3 inputs as 3 vertical lines, and the invert or the reverse or the opposite of these 3 inputs, we draw them in the parallel direction with the original 3 inputs, right? So here we have 3 inputs and they are reverse, right? This is A, this is A bar, this is B, this is B bar, C bar, and C, right? Alright, so the first logic input or the first logical product is A bar, B bar, C bar. So we need an AND gate, and 3 inputs are A bar, B bar, C bar, right? And as we mentioned the last time, if there's no dot on a cross line, that means these 2 lines are not touched, right? So the output is A bar, B bar, C bar. That's the first term. Alright, the second term is A bar times B times C bar. So we need A bar, which is this one, times B, which is this one, and C bar, right? C bar is this line. Okay, 3 inputs together, the output is A bar, B, C bar. Alright, the third term is A, B, C bar. So we need A, we need B, and we need C bar. This line is C bar, right? So the output is A, B, C bar. Alright, the last term is A, B, C. So we need the original input A. There's a dot here because these 2 lines are touched. We need B, and we need C. C is this one. Okay, so it's gonna be a long line to here. Alright, okay, and that's A, B, C. Alright, so the last step is we just need an OR gate to sum them together, right? The functionality of OR gate is logic sum. The output is F. So that's how we draw a logic circuit to realize, to implement this logic expression. But as you can see, this logic circuit is not simple. It's not easy to draw, right? And if you do that on the homework, or if you design a logic circuit and you show your design to other people, this logical circuit may not easy to follow for other guys, right? For other people. So, is there a way for us to simplify a logical circuit before we draw the logic expiration? Some people will say, well, we have, right? Because we have the De Morgan's law. De Morgan's law is exactly designed for that purpose. We have break the line, change the sign law or De Morgan's law, which can combine the common terms and cancel or remove some terms. So the final result is gonna be easy. But if I just give you the truth table, can you do that job with the De Morgan's law? Or is there an easier way to do that job without using the De Morgan's law, right? So that's our focus for today's class, which is the kernel map. Or K-map. Okay. So the functionality of K-map or kernel map is we can quickly simplify. We can quickly simplify a logic expiration with graphical method. All right. For instance, if I give you a truth table, okay. If I give you a truth table, let's just use this example, okay, because we already have this truth table. Okay, so let me copy this truth table, so I don't need to redraw it. All right, let's say we have this truth table, and then according to this truth table, we can find the simplest logic expiration by using kernel map, by using K-map. So how to do that? The first thing I want to introduce is first, according to the number of input, draw a blank K-map. Okay, so what that means? For instance, here we have 3 inputs, right? So we need to draw a 3-input K-map. As long as the number of inputs is determined, the format of a blank kernel map is also determined. Okay. In other words, if you have 3 inputs, then no matter what output is, the 3-input blank kernel map is always in the same form. It's always look like the same. Okay. All right. So let's draw a blank 3-input kernel map. Let's put to draw a blank 3-input kernel map. The representation is something like this. Okay. We put 2 inputs on one side and put the other one on the other side. Okay. So let's put A, B on the top side and put C on the bottom side. Okay. And then we list all possible input combinations on the corresponding row or the corresponding column. So what that means? For input A and B, all possible input combinations are 0, 0, 0, 1, and here is the tricky one. The next one, instead of 1, 0, that should be 1, 1, and the last one is 1, 0. Okay. For the input C, 2 possible inputs are 0 and 1. The tricky one is this guy, right? Instead of 1, 0, it is 1, 1. Why? Because there's one important row rule to draw the kernel map. Two consecutive rows or columns are different with one digit. Okay. Alright. So here, the reason why we put 1 1 here is exactly we need to follow this row. Because 0 1 and 1 1, if you compare these two combinations, 0 1 and 1 1, there's only one digit different, right? Which is the first digit. And if you compare 1 1 and 1 0, these two combinations, there's also one digit different, which is the second digit, right? So all rows and columns are different with a single digit. That's an important role for the kernel map. Or after that, we finish the blank kernel map. And as you can see, we have, according to 3 inputs, we have 8 blank cells, right? And we need to label these cells with the row numbers. Okay, so what that means? That means for the first row, inputs are 0. For the first cell, the inputs are 0 0 0. So the corresponding row number should be 0, right? The second one, 0 0 1, the row number should be 1. The row number is equivalent to the cell number. Okay. Alright, for this cell, the inputs are 0 1 0. And if you translate that, or if you convert that to a decimal number, that's 2. So this cell number should be 2. This should be 3. And the tricky one is this one, 1 1 0. The corresponding decimal number is 6. So the cell number here should be 6. And this is 7. This is 4. And this is 5. Okay. Right, after we finish labeling these cell numbers, the next thing we need to do is we need to fill ones into the blank kernel maps. So how to fill ones? Which cells should have 1? That is corresponding to, that is based on the output of the truth table. Okay. And as you can see, we have row 0 is 1. So in the corresponding kernel map, cell 0 should be 1. Okay. And row number 2 is 1. So the corresponding cell 2 is 1. And row number 6 is 1. Cell number 6 is 1. The last one, row number 7 is 1. Cell number 7 is 1. And for all other cells, they are 0, right? Alright, after you finish filling ones into the kernel map, the next step is also very important. We need to circle these ones, okay? And the rules of circling is rules of circling. The first rule is we can only circle the number of 2 to the power of n cells. Okay, and this n is 0, 1, 2, 3, 4, 5, 6 integers. Okay, so what that means? That means you can only circle 2 to the power of 0 cells, 2 to the power of 1 cells, 2 to the power of 2 cells, and 2 to the power of 3 cells, and so on and so forth. So the corresponding cell number is 1, 2, 4, 8, and so on and so forth, right? So for here, we have 4 cells are labeling with 1. So, and as you can see, we have 3 ones in the same row and a single one in the second row. But if you look at vertically, cell 6 and cell 7 are also in your same column, right? So that's the first row of circling. The second row of circling is we circle consecutive ones together. Okay. So far we have introduced two rows. The first row we circle 2 to the power of n cells together. Second, we circle consecutive ones together. Okay, so in the first row, in this example, in the first row we have 3 consecutive ones, but 3 is not a possible number of circling. So we can only circle them in this way, right? We can only circle 2 ones together. Okay. Alright, so that is based on these two rules. Alright, and also we have the third rule. The third rule is we use circles to cover all ones in the kernel map. Okay. And here we have cell 6 and cell 7. These two cells are consecutive or are neighborhood, right? So we can circle these two ones together. And after these two circles, we satisfy the rule number 3. We use 2 circles to cover all ones. Okay, and then we can finish. But there's a fourth rule, which is all corners, all boundaries are consecutive. Okay, so what that means? That means this boundary is consecutive with the bottom one, and the left is also consecutive with the right. Okay, so if you imagine the kernel map as a piece of paper, then we can roll this paper as a cylinder, right? So if you roll a paper as a cylinder, then the two edges are touching together, right? And we can roll a paper in 2 different directions, vertical or horizontal. Then these 2 boundaries are touching together, right? So the corresponding 2 boundaries or 2 edges are touching together. So that is exactly how we understand rule number 4. You can imagine the kernel map as a piece of paper. Okay. All right. So these are 4 rules that we should follow in the circling. For rule number 4, let me give you some examples. For instance, if this is part of the kernel map, this is 0, 1, this is 1, 1. If we have 4 ones like this, then for the circling, as I mentioned in the rule number 4, top boundary is consecutive or is neighborhood with the bottom boundary. So we can circle these 2 ones and these 2 ones as a single group or as a single circle, right? And for another example, if we have this scenario, okay, this is 0, 1, okay, 0, 1, 1, 1, let's say, if that is the situation. We have 2 ones on the left, 2 ones on the right. Then we can circle these 4 ones as a single group because 2 vertical boundaries or 2 vertical edges are consecutive or are the neighborhood. Okay. Alright, and the last row is also very important, and I want to introduce the last row. Lastly, rule number 5, circles. Circles are allowed to overlap each other. Okay, so what that means? That means if you have a situation like this, yeah, let me use the green color to draw kernel map. If you have a situation like this, okay, and then you can circle these 4 ones together and these 4 ones together, okay, and you see if I label this as circle 1, this is circle 2, these 2 circles are overlapping to each other, right? So why we need circles to overlap with each other? Because that is the rule number 6. We need to circle as large. Let me put it this way. Create the circle as large as possible. Okay, as large as possible. Okay. Right, so those are 6 rows in the kernel map, and you may not familiar with the kernel map at this moment, but I'm gonna show you 2 more examples, and after these 2 examples, you guys will be more familiar with this tool, with this concept. Okay, I'll give you another example. But before I introduce this example, I want to introduce one more thing, which is another representation of the truth table. Okay, here, as you can see, in this truth table, if we know the number of inputs, right, then we can determine how many rows in this truth table. And also, if we know the rows that are outputting 1s, then we can determine the entire output, right? Because for the truth table, the output either be 1 or 0. If we know which rows are outputting 1, then the left rows or the remaining rows are outputting 0, right? That's like flip a coin. It either be one side or the other, right? All right, so another way to draw or to represent the truth table is we just tell the people how many inputs we have, and we just need to tell the people which rows are outputting 1. Okay, so this truth table can be represented by another representation. It's called the SOP expiration. F is equivalent to sum of product and 0, 2, 6, 7. Okay, so let me explain. This expiration means SOP, sum of product, means we can write this logic expiration in a sum of multiple logical products. Okay, and these, inside these parentheses, they are rows that output 1. Right, we have 4 rows that are output 1, so we write 4 row numbers inside these parentheses. If you compile the entire truth table to this single line expiration, you will find the advantage of using this single line, right? It's more compact and it's more concise to express, to represent your idea. Alright, so here in this example, let me give you the logic product expiration. Sum of product, and inside parentheses we have 1. I'm sorry. I missed one thing in this expiration. I forgot to indicate how many inputs we have, and that information is inside. It is on the left side. Okay, and inside these parentheses, F ABC means in this expiration we have 3 inputs. Okay. And in this example, I'm gonna show you how to handle 4 inputs. Okay. Here F, A, B, C, D, we have 4 inputs, and sum of product is 1, 3, 4, 5, 7, 10, 12, and 13. Okay. So here in this expression, this is equivalent to a logic expression, right? If first, it is equivalent to a truth table. Second, it is equivalent to a logic expression, because after we have the truth table, we can use the synthesis of logical circuit to draw the corresponding logic expression, right? And after we have the logic expression, we can draw the logical circuit. So here, we have a 4 inputs truth table, and the sum of product, it is presented in the sum of product way, and those are rows are outputting 1. Okay. Alright, so without further talk, let's draw the blank kernel map first. Okay, here is a new kernel map because we have 4 inputs, but it follows the same rules. We put 2 inputs on one side and put the other 2 inputs on the other side. So like this way, A, B, and C, D. Okay, and we put possible input combinations on the row and column, on the initial row and the initial column. So in the initial row, they are 0, 0, 0, 1, 1, 1, and 1, 0. For CD, we have 0, 0, 0, 1, 1, 1, 1, 0, which is identical with the initial row, right? Alright, after this step, So after this step, we also need to label the number of cells, starting from 0, because it is according to the order of ABCD. The first cell is 0, 0, 0, 0, and the decimal number is 0. The second one is 0, 0, 0, 1. Decimal number is 1. Here the tricky one is this one. ABCD, in the order of ABCD, this cell is 0, 0, 1, 1. The decimal number is 3, and this one is 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so that's a blank kernel map for 4 input. Okay, and then we need to fill ones in this blank kernel map. One thing before I fill ones into the kernel map is I always recommend you to draw a blank kernel map on your notebook, either be 4 inputs or 3 inputs. Okay, because you don't need to think about, or you don't need to redraw a blank kernel map when you have a question like this. You can just use the blank kernel map on your notebook. Right. Alright, so here we have A, B, C, D as the here we have these rows are outputting ones. The first one, row 1, row 3, row 4, 5, 7, 10, 12, 13. Right. Did I? Yes. That's all rows are outputting ones, right? And then we can circles. We have 6 rows to. We have 6 rules to need to obey when we circle ones, but in a simple way to summarize these rows is first we need to memorize that we need to circle ones in the number of 2 to the power of n, right? And also we need to circle consecutive ones. We need to circle as large as possible. Okay, So here we have 1537. These four cells are consecutive, and they are in the they can be circled in a single group. This is also in a single group. And here we have cell number 10. It's a single one, and there's no consecutive ones with cell number 10. So we just need to circle this single one as a single circle. Okay. Alright, after circling, you see we have 3 cells, and we just need to represent these 3 cells with the logical product. Let's label these 3 cells first. These 3 circles first. This is circle 1, circle 2, and circle 3. So how to represent circle 1? Circle 1 occupies for AB, it occupies 0, 0, and 0, 1. For CD, it occupies 0, 1, and 1, 1, right? And then we just need to find for each AB and CD, we just need to find what is the unchanged variable. Okay, for AB, you see A is the unchanged variable, and A is always 0, which means the inverse of the input. So that's A bar. And for CD, what's the unchanged variable? That is D, and D is always 1. So the result gonna be D. And then the representation of circle 1 is just A bar times D. Okay, it's a logical product. And for cell number 2, we repeat this process. AB, AB are 0, 1, and 1, 1, because circle number 2 occupies these 2 columns, right? And the unchanged one is B. B is always 1, right? And for CD, it occupies 0, 0, and 0, 1. The unchanged one is C. C is always 0, which means it's C bar, right? And put that together, that's BC bar. And for the last circle, circle number 3, AB is 1, 0. CD is 1, 0. Okay, and you see ABCD, there's no changing variable. Both AB and CD are unchanged, which means A is 1, B is 0, so that's AB bar. And for the second one, C is 1 and D is 0, so it's CD bar. Okay, so put them together, it's AB bar, CD bar. And put everything together, F, the final result is gonna be A bar D plus BC bar plus AB bar CD bar. Okay, so that's the logic expiration. And if you compare this method with the original method, which means what does original method mean is the synthesis of logical circuit. We have 8 different rows, or let me see. Yes, we have 8 different rows outputting 1. In other words, if we follow the original method, we're gonna end up with a very long logic expression. But here, after using the kernel map, the logic expression is simplified to 3 terms, and to draw the corresponding logical circuit, 3 terms is much easier than the 8 terms, right? In terms of the number of turns. Okay. Right, so that's the kernel map, and that's the main topic of today's class. Let me know if you have any questions. Okay, and also after today's class, I'm gonna give you the homework of this chapter. In the homework, there's also a kernel map question. Try to finish that question by yourself, and if you couldn't, if you still feel confused about the kernel map, let me know. Give me a message. Give me an email, or you can also Google this topic on the internet. There's some fantastic examples on the internet too. So either way, you can either ask me or figure it out by yourself. Okay. Alright, have a good weekend, and I see you guys next time.